well-defined value should we,
Yes.
or we can take any values?
Any values cannot be taken. So there is a, as you have seen in the Hamming bound, so any
Yes.
value of n comma k cannot be constructed as a block coding. Right? They have their own properties. I have listed couple of properties of block coding as well.
Yes, sir.
So random values of these n and k cannot have cannot be called as error correcting codes. So there is a procedure where you can actually make use of Hamming bound, where it strictly says that this 2 power 2 power m should be greater than or equal to the
Symbol.
t representing the number of symbols which can be corrected, n c j, right?
So
So this
any
was
values
actually,
above
this
the
is
upper
actually
bound.
exactly.
So
Okay,
that upper
so this
bound is,
strictly if it upper bound is 2 power m. I mean, there is no upper bound. I mean, the lower bound is equality,
lower.
where yeah, so that is itself is a lower bound. If it is greater, 2 power m is greater than this summation, then you will be over satisfying this Hamming bound. The implication of over satisfying the Hamming bound would be, you will not only can decode all the t errors in the transmitted codes, but also you can detect and correct few t plus 1 or t plus 2 codes as well. Okay, so strictly speaking, if it is equal, you can correct up to detect and correct up to t number of errors. If it over satisfies, in the sense, if it's 2 power m is greater than this summation, then you can just not detect and correct t errors, but also few t plus 1 and t plus 2 and so on. Only few, I'll say, not all. But t, definitely you can find out all errors and correct them as well. Okay, that's with that, you can construct actually any block codes.
yes. Is there a name
Okay.
for these pairs which satisfy exactly the bounds?
That's Hamming code. It's where the code which exactly satisfies this inequality is called as Hamming code, or we can say perfect codes. Perfect codes are the
Perfect
ones.
codes.
Yeah, perfect one. Hamming code is one type of it, where Hamming codes are specifically which correct detect and correct t as equal to 1. So single error correcting codes are called as Hamming codes, and those Hamming codes are called as perfect codes because of satisfaction of equality. Okay. Yeah,
Yes,
so
sir.
with that, I think somewhat vaguely you understood what's happening in a later part of this CS1 course, but nevertheless we should solve few numerical problems before actually getting into the specific questions. What we have not done as source coding is Shannon-Fano coding. Okay, I'll just cover that before we get into the other parts. I hope spilling over more than 1.5 hours is okay with everyone, because it will take at least of 1.5 hours. Okay, so we'll cover most important questions of Unit 4 and Unit 5. I believe that should be fine with you all. Okay, so Shannon-Fano coding, as far as its algorithm, it's very similar to Huffman coding that we have done in the earlier part of Unit 4. So let me try to explain the algorithm first, then take a case or specific example. So it's similar to the Huffman coding, where you will list the source symbols. You will list the source symbols in order of decreasing probability. Okay, that's what we are done, right? Decreasing probability. That's the first part that you are going to do, given the probability distribution of all the symbols. Then, unlike Huffman coding, we are not going to group last two symbols with the least probability. However, here there would be a partition made. Okay, the source set into two sets, into two. Sorry, here it is. The partition the set into two sets. Okay, how we will be partitioning is based on that are as close to equiprobable as possible. Okay. So these partition of the two sets should be such that the probability of each set should be equal, or it should be as close to equiprobable case. Okay. So after partitioning, then assign 0 bit 0 to the upper set and bit 1 to the lower set. Okay, that's a second step. Third step is just to repeat. I can say there would not be, again shuffling of all the symbols would happen because it's just partitioning. So I can just say repeat step 2. Okay, each time partition the sets again with nearly equal probabilities as possible until no further partitioning is possible, until no further partition is possible.
Sir,
Okay, this is a generic algorithm. Yes, please.
and, sir, so
Yes.
is there any threshold beyond which we can say no, these are not equiprobable, and like below that we can say yes, these two are equiprobable?
That's good question, but Dipta, I can say that there is no specific value that is mentioned in the Shannon-Fano coding. It is just the intuition. Okay, you can get different encoding sets as probably depends on the nature of the problem as well, nature of the probability distribution, but more or less the intuition as I have seen in my in practice, I don't think you would get different encoding all of it different encoding sets compared to other. More or less it would be very close to each other. You probably there is very rare chance that you would be getting different answers to a single question. Okay, but your question is right, definitely is right, because there are chances of getting different answers or different encoding sets, but you will see it's specific to few problems. If the distribution is very vague, then definitely there could be possible of grouping in more than one ways. So then the problem of having singular answer would be difficult. Otherwise I can say that in most of the cases you would arrive at single answer.
Okay, sir. Thanks.
Okay, so okay, I'll take specific example. Say xi is the input symbol, right? So I can say there is x1, x2, whether it could be discrete or just the samples of continuous memoryless source. So if there are 6 message symbols with their individual probabilities as say 0.3, 0.25, okay, 0.20, point say 12, 0.08, and 0.05. Okay. All right, so with that, we'll get on to the first step where we need to partition according to as close to equiprobable. As you can see, the first probability is 0.3, and obviously the sum of rest all is 0.7, which is not so equal to each other. So, and if you take another probability, say 0.3 plus 0.25, this would be 0.55, and another set would be the rest of all symbols, so which will come out to be 0.45. Say if I take first and if I just extend my assumption, say I'll club first 3 symbols, I'll group first 3 symbols and other 3 symbols as another set. The first 3 groupings, the probabilities would result in more than 0.75. I mean, it's more 0.75 exactly. The other group would result in 0.25. So compared to other 2 partitions, the intuition here is the combinations of x1 and x2 symbols as one group and x3 to x6 as another group would give me a probability which are approximately close to each other. Okay, so with that I can say I can put a partition here, and as per the algorithm I have to assign I have to assign bit 0 to first group and bit 1 to the second group, the lower group. So if I assign 0 and 0 to this group, 1 1 1 1 would be the representation or the encoding for the second group, right? So again we have to subdivide into each group. So there are only two elements here. That's very easy in step 2, because there are only two symbols. I have to just split into two parts. So this will result into two parts, which would give me 0.3 and 0.25 separately, which I can say it as more or less close to each other. And again I have to give 0 to the upper set and 1 to the lower set. Okay, coming down to the second group, again there are more possible cases here of grouping. And if I say this x3 has a probability of 0.2, and the combined probabilities of x4 to x6 symbols would give me 0.25. Okay, so 0.2 and 0.25 would be treated as as close to each other, and I can just have one group of these, and I'll assign 0 to the upper group and 1 to the lower groups groupings. Okay, so 0 is written as it is, so there are no further divisions that is possible. So first two symbols are done, since these will take 0 and 1 respectively. Even third symbol is also done with. All we need to take care of the three symbols at the bottom. So again, looking at the probability, x4 has 0.12, x5 and x6 combined has 0.13. So partitioning here would result in 0, 1 and 1, and finally we are left with just two symbols as step 4, and we can straight away split them as 0 and 1. Okay, so with this final encoding of this would result in, the code would result in x1, as we have given as 0, bit 0 would be the representation or the coding of symbol x1, and for x2 this would be 1, and for, sorry, I make a mistake, yeah, so I have to trace from the left hand side. So 0 and 0 combined together will be the code of symbol x1, and 0 and 1 would be the combined code of step 1 and step 2. And for x3, again similar with that case, this is 1 0, and for x4 this is 1 1 0. It has reached up to step 3, so this will have encoding of 1 1 0, and similarly last three symbols would get the code as 1 1 1 0, and the last would be all ones. Okay, it's very similar to Huffman coding, which is another class of variable length code, but the procedure or the algorithm is a little different as compared to the Huffman coding. Okay, so this, yes, please.
Sir, so basically in step 1 we have two zeros, and then we're partitioning that into like 0 and 1. So what if there's more than 2?
In the first group?
Yes, sir. What if there's more than 2 zeros? So let's say it's
Okay.
0 0.
Right. I mean, the sense in the sense, if your question was something like this, I mean, if I don't partition x1 and x2, if the probability distribution is such a way that I club these x1 x2 x3 as one group and x4 x5 x6 as another group, then I would end up with three symbols here. So ending up three symbols again, in step 2 I would partition into two groups again. So that would run till step 3, and I would get 3 bits for even for x1 and x2 symbols as well. It depends on how these probabilities are distributed over the sample values.
Okay, sir.
Okay. You would be asked to find out, just not for encoding, you would be asked to find out the entropy of the source as well. As you know, the entropy is pi, we represented the total probability as capital P log 1 over pi. Okay, since the probability distribution is already given to you, you can easily find out the entropy of the system. Okay, Yeah, remember this is log base 2 that you might have already seen in your previous test in case of Huffman coding. Right. So you would ask to find out the average length. Average length, as you know, is again summation of the length of each code times the probability of individual source. So this again runs from I1 to 6. This is I1 to 6. Right. So length of the each code is not uniform. So you can just pick from the length of the codes from the final code table and try to plug in their lengths and multiply with individual probabilities. That would result in the average length, which comes out to be around 2.38 bits per symbol. Okay, again, h of x is almost approximately equal to length, which would give me the efficiency close to 1, right? Since there is no redundancy here, so efficiency, the code efficiency, would be by definition h of x over L. So this is almost close to 1, around 0.99 would be the result of this. Of course, redundancy, we know that this is gamma, which is 1 minus eta, which is 0.01. Okay. So this was part of your unit 4 initially. We started off with Huffman coding, but usually the case with that after understanding the entropy, the efficiency and redundancy, you would begin with Shannon-Fano and then pick up Huffman coding, which is more systematic. But however, it was missed from my end in the last unit. Okay, so this is included as part of your test 3. I will discuss about test 3 portion and the nature of the questions at the end of this tutorial session. Don't worry about that. All right, so let me get into more specific questions now. Let's consider a binary channel. This was explained in the theory. So this is known as binary symmetric channel, BSC in short. Okay. Binary symmetric channel. Probably this is not symmetric because of unequal probabilities. Okay, let me not call this as symmetric. Okay, anyway, so this indicates that x1 and x2 are the transmitted symbols which are transmitted over a noisy channel. Y1 and y2 are the received symbols. 0.9 indicates probability of y1. So probability of receiving x1 given y1 is 0.9. All right, so I'll just list down those probabilities. This would be more clear. Based on the given binary channel, I can list the probabilities given. I would get the probability of y1 if x1 is transmitted is given it as 0.9. Similarly, probability of y2 given x1 is 1 minus 0.9, which is 0.1, which is given directly in the representation of this channel itself. Then probability similarly of y1 if x2 was transmitted, probability of y1 if x2 was transmitted is 0.2, and probability of receiving y2 if x2 was transmitted is 1 minus 0.2, which is 0.8. Okay, so this is the mathematical representation of the binary channel which is shown. We need to find out the channel matrix. As I have told, the channel matrix is represented by the a priori probabilities. The channel matrix, okay, is represented by a priori probabilities, which is actually a matrix which is represented as probability of y given x, right? So obviously this will have four elements. Each of the elements is represented by the priori probabilities which I have already written. Y1 given x1, probability y2 given x1, and probability receiving y1 if x2 was transmitted, and probability of receiving y2 if x2 was transmitted. Okay, So you can easily construct the channel matrix based on the value that we have noted from the given diagram. Okay, so this will constitute the channel matrix. Pretty straightforward.
So
All right.
why
So
is
the
it,
part,
or
yeah,
so
yes.
why is it called channel matrix and why is it priori probability?
Priori probabilities means that before, this is the probability uh, of receiving y1. Say that, I know the probabilities of x1 and x2. I know as a transmitter side, I'm throwing x1 into the channel. It can be received as either as y1 or y2 at the receiver, because this is only binary case, right? So again, I repeat, I'm throwing the symbol x1. It could be received as either y1 or y2 due to noise in the channel. Okay, so if it is received as y1, what is its probability? So in the sense, I'm sitting at the transmitter and I'm just in prior of the transmission itself, I'm just trying to find out what is the probability of sending x1 if y1, if the receiver would treat it as y1. It's a reason it is called as priori probability, because before hand itself I'm trying to measure its uncertainty. And it is called as channel matrix only for the fact that this is a probability which is uncertainty is involved due to the noise in the channel. This is these probabilities, condition probabilities are directly governed by the noise associated with the channel. Okay.
Yes, sir. And
Okay.
x by y will be posterior probability.
Yeah, x by x given y would be, I mean, it's a condition. I'm putting a condition that I have received y for a specific value of y received or decoded. I'm trying to map it onto what actually been sent from the transmitter.
Yes, sir.
Okay, this is the posterior probability after receiving the received symbol. This will that's good that you have asked the question, because this will be again taken into consideration in your communication system too, as a first unit itself. Probably the second half of first unit, where we would be trying to maximize all these condition probabilities as maximum likelihood estimation, as MLE. Okay, so this would be definitely taken again there. Good that you understand these concepts in a better way. All right, so next part of the question here is finding out a probability of y1 and probability of y2 given some specific symbol probabilities. Okay, so probability of y1 that from, in general, I can say that in general probability of y, which is the probability of received symbol, in general can be, I'm writing this in square brackets because this is a distribution and it has got multiple values, because there are y1 and y2, so there will be two elements in P of y. It's a row vector. Okay, so this is known by the product rule, which is P of x times P of y given x. Okay, so based on the simple product rule that we know from probability theory, this can be represented in this fashion. So we know that probability of x is will have two elements. One is probability of x1 and probability of x2 multiplied by the conditional probability that already we have written as 0.9, 0.1, 0.2 and 0.8. Okay, so with the given probability values, which is 0.5, so these are equiprobable in this case. So for both symbols of 0.5 probability, all we need to just multiply the matrix. Okay, so this would result in, the left hand side is probability of y1 and probability of y2 are the two elements. So this would result in 0.95 into 0.45 plus 0.01. Right, so this would result in 4 combinations. So first element would, sorry, so this is a row vector, there will only be two elements here. A 0.45 plus 0.01 would give me 0.55, and next multiplication will give me 0.5 plus 0.4, which is 0.45. Okay, so this is the required the probabilities at the receiver. All right. So finally, we are asked to find out the joint probabilities as well. So again, the joint probabilities would come in 4 types, since there are 2 inputs and 2 outputs. So probability of x1 comma y1, x1 comma y2, and x2 comma y1 and x2 comma y2 are the 4 different joint probabilities. But we are asked to find out just 2 values. But since we are multiplying the matrices themselves, we will get all the elements. Okay, so we know that probability of xy, which is a joint PDF, which we know this can be represented as p of x times probability of y given x. Okay, probability of x is known to us, but probability of y given x, this is a 2 cross 2 matrix, the conditional probability that we have written. Probability of x comma y, that we know there are 4 elements here, so we expect 2 cross 2 matrix on the left hand side. So p of x is not a row vector now. Okay, so p of x supposed to be having just 2 elements, but 1 cross 2 times 2 cross 2 matrix would result in just 1 cross 2. So we would not be getting 2 values of the joint probability probabilities. So because of that fact, we can rewrite this as 0.5, 0 and 0.5, saying that 0.5 represents probability of x1 and this 0.5 represents probability of x2, which in the given question are equiprobable. Okay, so with that, I rewrite that channel matrix, and now you will get all the values of the joint probability. Okay, so if you multiply, this would give me 0.45. Yeah, this would give me 0.05 first row and second column, right? The second row would be simply 0.1 and this should be 0.4. Okay, so this is probability of x1 comma y1, this is x1 comma y2, and so on. So we are asked to find out x1 y2 and x2 y1. Okay, so this implies x1 y2 and x2 y1. This would be the second element. X2 y1 would be the first element in the second row, is 0.1. Okay, all right, so that's about binary channel. It's not symmetric because of the asymmetric probability errors in transmitting symbols x1 and x2. There could be another type of a channel, okay, where there are 2 symbols which are transmitted from the transmitter end, and you may receive 3 symbols at the receiver. Okay, so this kind of matrix is known as binary erasure channel. Okay, in short, it is called as BEC. Let us try to draw the channel diagram here so that it will be easy to understand. So based on this matrix, based on the input relation of probabilities of input and output symbols, we can draw the channel picture itself, where this is x1. I say bit 0 is transmitted since it is binary. So bit 1 is transmitted as x2, and as I told, there would be 3 symbols which is received at the receiver. Okay, so this is y1, which is 0. So this is y3, which is 1, which is bit 1. But there could be a middle symbol which could also be received, and we regard it as an error E. If it is neither 0 or nor 1, if you are not able to make proper decision, then we could call it as E. If it probably in your circuit sense, if it exactly at the middle of your threshold voltage of the MOS itself, whether you will not be able to decide whether it is 0 or 1, we will try to keep a status or keep a state for that symbol as well, that kind of sample values as well. If that is the case, then this is the binary erasure channel. Erasure because we'll eventually erase such values at the receiver. We'll try to eliminate such values at the receiver, but there would also be certain probabilities of of having such values lying exactly at the threshold. Okay, so that will have three probabilities as designated in the channel matrix itself. Say probability of y1 if x1 was transmitted, so that is given as 1 minus p as for the matrix, and receiving y2 if x1 was transmitted, that is regarded as probability p, and there is no chance as for the matrix to receive 1 if 0 is transmitted, and there is 0. I will not represent. So if there is no probability, I can eliminate this representation in the channel diagram. Okay, so what non-zero values others exist? So for other set where the second row is x2 and the first column is y1, again this is 0 probability, so this line joining x2 and y1 would not be there. However, for other values, other combinations, I have a non-zero probability. Say for receiving y2, okay, so if x2 was transmitted, this is with probability p, and finally I say that receiving y3 if x2 was transmitted, this will occur with 1 minus p probability. Okay, all right, so with that I can say this E indicates erasure. Okay, all right, so that's the channel diagram that is asked, and the second part of the question is that if the source has equally likely outputs, compute the probabilities associated with the channel outputs for specific value of p. So this is again the similar treatment of binary channel, symmetric channel that we have seen earlier. So p of y is given as p of x times p of y given x. So p of y given x is a channel matrix which is already given to us in the problem itself, and p of x is given as source has equally likely outputs. Then obviously we have 0.5 and 0.5 as the probability at the source, and just multiply with the channel matrix. For the channel matrix, p is specified as 0.2, and with that specific value we would have 1 minus p as 0.8, this as 0.2, 0, 0, 0.2, and finally 0.8. Okay, so multiplication of this matrix would give us, okay, this is 0.4, 0.5 times 0.2, 1, 0.1 plus 0.1 is 0.2, and this is 0.4. Okay, it's the left hand side. Remember, this is probability of y1, y2, and y3. Okay, so these are the elements or the probability of receiving the outputs y1, y2, y3. Okay, so this is with respect to binary symmetric and binary erasure channels. Okay, so this is actually done in the one of the textbooks which is prescribed as BP Lati, but I thought of taking this in the tutorial part such that this is more clear. Okay, let's consider a binary symmetric channel. Now the channel is symmetric where y1 given x1 is 1 minus p and y2 given x2 is also 1 minus p. Since it's a symmetric case, we call such a channel as a binary symmetric channel. We have to find out the mutual information for such channel. Okay, so after proving this, after finding out that mutual information is related with h of y and the p's or the probabilities indicated in the channel, we'll calculate the mutual information for specific alpha and specific value of p as well. And finally, we'll also extend this question to calculate the channel capacity. Okay, so that again, this is an important part as far as your test and your quizzes are concerned. Let me try to derive this. Okay, we have so 220, around 220. That's fine. We can spend 10 minutes to derive this expression. All right. So from channel matrix, we have, let me write the channel matrix first, which is probability of y given x. This is a priori probability, which is indicated by 1 minus p, 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 and 1 minus p. Okay, so probability of x. All right. So to find out mutual information, first we should find out, I mean, since we have the expression of mutual information, since it's a symmetric, we can write this as h of x minus h of x given y, or we can write as well this as h of y minus h of y given x. You can make use of any of these two relations. Okay, so find out the mutual probability first. The mutual, or we call it as joint probability. Okay, let me stick to the same definition. The joint probability, which is given as probability of x comma y, is nothing but probability of x times probability of y given x, probability of x, as we have done in case of one of the binary channels in the second question as in the tutorial. So here this is probability of x1. Probability of x1 is given as alpha, so I'll just take that as alpha. This is 0, 0, 1 minus alpha. The channel matrix is 1 minus p, 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 and 1 minus p. Okay, so this would result in the product of these two matrices would result in the first element would be alpha times 1 minus p. 0 times p is 0, and next element is just simply alpha p, and this would be, again, this is second row first column. Yeah, so this would result in 1 minus alpha times p, and the last element would be 1 minus alpha times 1 minus p. Okay, so these are actually the elements of probability x comma y, which we call it as probability x1 y1, x1 y2, x2 y1, and x2 y2. Okay, so these are all joint probabilities. Therefore, I can find out the conditional entropy h y given x, because ultimately I want to find out the mutual information. So h of y given x, as far as your the equation that we have done in case of both discrete and continuous memory channels, it is summation of, anybody quote that if anybody is aware of it, or I have gone through the videos. The condition entropy h of y given x.
Joint probability matrix into log of 1 divided by conditional probability.
Okay, but we have written in terms of the a priori probabilities.
In terms of sigma.
Yeah, that's there. Or otherwise, I can say is, for since it's a case of discrete channel, as you rightly said, so summation, as I said, this is probability of x comma y, I mean the joint probability, times log 1 over probability of y given x, right? Okay, so with that I can find all the combinations where I is running from 1 to 2, j is running from 1 to 2, and of course this is xi, yj's and so on. But since in general I have written this, it is just combinations of all those, right? So I take the individual probabilities now. Probability of x1 comma y1 times log of, should be total probability, log of p 1 over p of y1 given x1, right? So y1 given x1 can be, okay, shall I write it directly, or how can I take directly from a channel matrix, or should I take another step to do it? Okay, I'll take another step to do it in order to avoid any confusions. Y1 given x1 plus probability of x2 y2 times log 1 over probability of y2 given x2 plus the other combinations x2 y1 log 1 over probability of x2 given y1. Sorry, so this should have been the other way around. Yeah, this is y1 given x2 plus x2 y2 times log 1 over y2 given x2. Did we miss any? X2 y2 are already covered, so this is x1 y1 x2 y2, or I can say here this as x1 y2. So to be make to more meaningful method of writing this, so this is y2 given x1, and hence the last combination is y2 given x2. Okay, so with that I can write this expression. Since I have already found out what is joint probability, I have all the 4 values in this summation, and I also have the condition probabilities as per the channel matrix itself. Say making use of this 1 and 2, I can find out the conditional entropy, okay, using h of y given x. In order to make this log, in order just remove this 1 over a, I'll take it in the numerator and attach minus sign everywhere to just to make it easy to write. So this would be, all terms would be minus here. So minus p of x1 comma y1. So x1 comma y1 is a joint probability which is alpha times 1 minus p times log of this conditional probability from the channel matrix, which is log 1 minus p. Okay, I'll just write this in a very quick way. Minus, similarly substituting from the known quantities, minus 1 minus alpha times p log p, and finally for the last combination you would have 1 minus alpha times 1 minus p times log of 1 minus p. Okay, so this can be simplified. This can be simplified by taking log of 1 minus p. Log of 1 minus p is a common term, log p is a common term, in fact p log p is a common term. You can club all these terms and can write this as minus p log p minus 1 minus p log 1 minus p. You can verify this. Of course the base of the logarithmic is 2. Okay, so this is conditional entropy. So therefore the mutual information I of xy that we know is h of y minus h of y given x, which we have h of y, because we don't know what is h of y. All we have found out is the conditional entropy, which is h of y given x. So minus of this term, this all terms are negative, and hence this would be plus p log p plus 1 minus p log 1 minus p. That's how you derive the symmetric channel. Okay, so we can extend this theory, although there is no question involved in finding out the channel capacity. However, we can find out the channel capacity with just one single step. Okay, channel capacity by definition C is nothing but what is the maximum rate of information transmission, maximum of this mutual information for a given channel. When the channel is known, then definitely P is known to us. So for a given P, the only term which is left here to maximize is h of y, right? So maximum of information is nothing but which will occur, okay, can say at maximum of h of y for a given channel. So what is the maximum value of any entropy? Can I have the answer? What is the maximum value of an entropy? I hope you are all there.
Said 1 by 2 log of 2 pi e sigma square.
Yeah. What's the maximum? In a different route. This is the case with just entropy, with the basic definition of entropy. H of y is summation of pi times log of 1 over py. So what's the maximum value that it can have? The minimum is 0, the maximum is 1. If there is no uncertainty, then definitely there is no information which is 0 itself. Otherwise it can take another extreme on the probability scale, which will give us entropy as unity. So therefore this implies that the maximum value of h of y would be 1. The maximum of h of y
Shouldn't it depend upon the
is 1.
probability
So this
distribution
implies
of
that definitely it will have a non 0 and non 1. It will lie between 0 and 1 for a non-uniform distribution of probabilities. But I am specifically asking what would be the maximum value of the entropy itself. Okay, h of y is obviously will happen when all symbols are equiprobable. So if I say h of y, you as this right decide this is pi times log 1 over pi. Okay, so this will have some value between 0 and 1 for any distribution of pi. If all the symbols are equiprobable, then I'll get a maximum entropy. Okay, there is so much of randomness, and I will not have any information about the transmission. That's what it means. Okay, so if there is little bias, say a simple case with your coin toss, where if both it's a fair coin, then I would not have any information whether head will occur or tail will fall when I toss the coin. But if it's a biased coin, then definitely the both head and tail will not occur with equiprobable. So there is some information involved in form of unbiasedness of the coin. Okay, so in other words, for equiprobable symbols, there would be no information. I mean, there would be the entropy would be maximum with the unity.
So that
Okay,
thing
so and hence this is
the right side that would have maximum entropy when all of them are equiprobable.
Right.
So
Right.
if I put
Okay, so pi is 1 over m.
1 by n,
Yeah,
1 by n,
1 by n.
then
What
it
would
will
this
sum up
be?
to log n.
Right. So how many elements are there?
Log n.
N elements are there, right?
N into 1 by n log,
Yeah.
log of n.
Log n, correct?
Yes, sir.
right?
Yes, sir.
Correct. Okay, so 1 over n. Pi, sorry, Pi is, I have taken it as 1 over n. So it's a binary case. If there are only two symbols which are transmitted, this is a logarithmic
Yes, sir.
basis 2. Correct.
Okay.
So n here is 2. So this would give us entropy as maximum as unity. That's what I was trying to say.
Yeah.
Okay. Okay. Yeah. Yeah. So this is a channel capacity per symbol, and hence the suffix s gets attached to this. So s is maximum when h of y is maximum, which is unity. So this will reduce to channel capacity as 1 plus p log p. Okay. So plus this, yeah, plus 1 minus p log of 1 minus p. Okay, this could be this is a channel capacity for binary symmetric channel. Same thing can be done for binary erasure channel as well. Okay, so please make a note of it. Say for binary, I have already uploaded miscellaneous questions on, or the set of questions on unit 4 and unit 5. You can find the derivation of these, of whatever I have done so far. I'm just picking few questions from those. So for binary erasure channel, if you are asked to find out in a similar way, mutual information would be 1 minus p times h of x. You have to do the similar process there. Maximum of this, so maximum of this, again here it's h of x, which would give take maximum value as unity. So this will be simply 1 minus p in case of binary erasure channel. So please uh, go through that part of tutorial, or collection of numerical problems on my webpage. I've already posted that. Okay, this is in generic case, but there are specific values that are given in the question. So if you want to calculate mutual information for alpha 0.5 and p 0.1, all you need to substitute those values into the generic expressions that we have derived so far. I hope that need not be done, because it's a very it's pretty straightforward case. Okay, just to make things clear, we are asked to find out mutual information for alpha 0.5 and p 0.1, since I of x y. All right, so with this I can find out h of y here. Okay, so I of xy that we have derived is h of y plus p log p plus 1 minus p log 1 minus p. Okay, h of y is the entropy for any entropy now, which is nothing but p of y times log 1 p of y, p of y2. Okay, small p is given, so we'll have to assume that p of, okay, we have to find out p of y because it's not given, right? So before applying this formula, we have to calculate p of y. So p of y is can be written as p of how can it be written as, yeah, this can be written as, let me think over this. P of y can be calculated as probability of x times probability of y given x. No, how can I write using a product rule? Point 0.5. Now let me just write and just check whether this is right. This is alpha is 0.1. alpha is given to be p is given to be 0.1 and alpha is 0.5. Okay, we have given with probability of x, right? So in the sense probability of x1 is 0.5, probability of x2 is 1 minus 0.5 is 0.5, right? So with probability of x known, we can calculate this as probability of x times probability of x, probability of y given x. Okay, so with that I have probability of x1 and x2 as 0.5 each, and y given x is from the channel matrix, which is 0.9, 0.1 and 0.1 and 0.9, 1 minus p and 1 minus p, where p is given to be 0.1. Okay, so this will give me the singular values of p of y, which is 0.5 and 0.5. Okay, so with this equiprobable of probability y, I can find out the entropy. So this entropy, again, I need not calculate since these are equiprobable. This entropy will be obviously B1. So this is a maximum information that is transmitted over the channel. Okay, so f so given, so which is 0.1. So this is 0.1 log 0.1 plus 0.9 times 0.9. Okay, so if you calculate this, you'll get some value. I'm not sure how about that. Okay, again, I'm sorry. So yeah, that's correct. This would result in negative quantity since it's log of 0.1 and log of 0.9. So 1 minus of that value, the mutual information would be lesser than 1. Okay. Similarly, you can extend this for alpha 0.5 and p as 0.5. You'll surprised to see the result here. H of y is similar with previous case, where in previous case also alpha as 0.5. Now p is also 0.5, in the sense it's again 0.5 between receiving x1 and x2 and receiving y1 and y2 and decoding it as x1 and x2. So with that case, your the conditional entropy will also become unity, in the sense h of y given x will be in fact minus 1. So this implies the mutual information h of y, okay, h of y, I'm sorry, so this will also maximum entropy 1. So minus h of, okay, so in this case no information is being transmitted at all, because an equally acceptable decision could be made by the channel entirely, and we can take a decision by just flipping a coin at the receiver. Okay, because of the equal probability of receiving both x1 and x2 at the receiver. All right, so and hence there is no information that is transmitted over the channel at all, and we say, surprisingly, we say the channel is said to be useless, right? So channel is indirectly helps in decoding the symbols in a right way, because if there is any error that occurs, then only there is something uncertainty that is involved. If the channel is unbiasedly working over all the symbols that is taken into it, then definitely it is not adding there is no loss of information, or there is no extra uncertainty that is involved in the channel. With that, we will not be able to decode the right what do you say, that symbol by the sampling at the receiver. Okay, so that's what this particular problem means. All right, so
So
on
if
with
it comes negative, then what would be the
sorry,
implications of
this is
that?
not negative, this is not
No,
negative,
no.
this is the entropy again.
I'm,
Yeah,
I'm asking if mutual information comes to be negative, and what are the
mutual
implications?
information mutual information cannot be negative at all. I think that is also told in one of the videos. H of y
Okay.
is the, in fact, you know that alternatively we write I of x comma y as h of x minus h of x given y. Okay, h of x is the source entropy. This is the origin of the information that is transmitted from the transmitter end. This is a maximum information. I mean, this is the reference with which we can say loss of information. Okay, the loss of information, this will always be positive, and hence I of x y is always be greater than or equal to 0. It's always a positive quantity. Mathematically, this also can be proved because h of x and h of x given y is just with the case of probabilities there. Okay, there is nothing like a negative information. Okay. All right. So let's switch on to the fifth unit, which I have. Just take few cases of block coding. Other related problems with respect to unit 4 is very straightforward, where you have seen the Shannon's channel capacity equation, where it is related to bandwidth and signal to noise ratio. Specific values of those would be given to you, and to calculate the channel capacity, which I'll take a conclusion at the end of this session. Give me some 10 more minutes of time to conclude this. I'll just take few questions on unit 5 and summarize and try to explain what you can expect from test 3 and quiz 3, of course. All right, so let's consider block code examples that have explained what is systematic code and what is non-systematic code. Non-systematic code is simple an extension of a systematic linear block code, where the since there are for systematic code are those codes where your I can say if D represents data digits, all DIs are equal to your CIs. Okay, for all I up to K. K represents number of data digits. I have done this in theory, don't worry about that. Then from CK plus 1 onwards, because there are n number of code word digits. Okay, so it will run from CK plus 1 to up to CN. Right, so from CK plus 1 onwards, all the code words are found by onwards code word digits are formed by linear combinations of data digits. This example states that, where since it is stated that it's a systematic linear block code, so this is N and this is K. So there are 3 data digits, original information digits, and which I'm encoding with expanding the data digits into 6 digit as code word length by adding parity check bits. So there would be 3 parity check bits which will lead us into 6 length of a 6-bit length of code words. So C1 to C3 is obviously D1 to D3, right? So with this understanding of systematic code, we can say that from C4 to C6, these are the linear combinations of the data digits. So we are asked to find out the generator matrix for such a specific systematic linear block code. All right, so I can write this generator matrix. We know that generator matrix is represented as, in general, as ik, which is identity matrix, and P, which is of the size k cross m, right? If I'm not wrong. So this is represented as, just check, let me check with the actual notations that we have used. This is ik, yeah, this is p k cross m. So overall, this will be the matrix of k cross n. Okay, so P is the parity check matrix, which should be find out in order to find out the generator matrix finally. So parity check matrix is found by the coefficients of all these linear combinations. Okay, so identity matrix is fine, but parity matrix is for all are generated by the coefficient which are multiplied by individual data digits. Since C4 is found by XORing D1 and D3, obviously the first row of the parity matrix would be D1, D2 is 0 and D3 is 1. Similarly, C5 is found by XORing all the 3 data digits. So with that, the coefficients would be 1, 1 and 1. And finally, D1 and D2 will form the code C6, and hence this is 1, 1 and 0. Okay, so this is a coefficient matrix, or also called as parity matrix. So with this we can construct the generator matrix now. In some cases, in case of linear block code, you'd be given generator matrix directly. Otherwise, you'll have to construct with the information given in the question itself. Okay, now I think I can form. So this is transpose matrix. I'm sorry, I'll make a point there. Let me check back with the representation. Ik, this is P. Yeah, this is found by, right, this is correct in notation. All right, so with generator matrix, the first remember, this is not the multiplication of these two matrices. This is an augmented matrix. I can just separate with the dotted lines there. So Ik, with the k is a size of 3 there. So this is 1, 0, 0, 0, 1, 0, 0, 0, 1. And next is transpose of this parity matrix. The transpose of this would give me 1, 1, 1, and 0, 1, 1, and finally 1, 1, 0. So this is your generator matrix. Okay,
I
that
don't
would be
think
the
so.
first
It's a
part of the.
transpose.
Well, just
Should
check. I'm
we
not
should be
finding
just
it.
be low?
Yeah, yeah, I can hear you. Okay, this should be P,
Yes, sir. In
and whatever I've written here is in fact is transpose. Please make a correction. Okay, because I've taken the codes in the row wise. Okay, I have taken C5 to be representing this. Sorry, C4 and C4 is this, code C5 is this, and this is C6. I should have directly written as a transfer of this. Since I already flipped this, that's the reason I'm just trying to adjust my answer to that. Okay, C4 I have written row wise, which is C4 is 1, 0, 1, right? D1 is 1, D2 is 0, D3 is 1. That's the reason I have written in a row wise fashion. That's the reason I have to attach in a transpose here. Otherwise, this is, as you said, this is I and P, as it is, right? Okay, so what else we are supposed to find? Construct all possible code words. Okay, that's right. The construction of all code words can be tabulated. Okay, so this could be your information digits, and this could be your code word as k tuples. So D, since it's 3-bit information digits, you can have 8 combinations: 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, and finally 1, 1, 1. So for all these 8 combinations of data digits, we can find out C by knowing the relation that C is nothing but D times G. Okay, so 0 0 0 times the matrix G would be obviously all 0 code. 0 0 1 would give me how much? 0 0 1 would be, it is simply the third row itself, right? 0 0 triple 1 0. 0 1 0 would be second row. 0 1 0 0 1 1. For 0 1 1, it's modulo 2 addition of the last 2 rows of the generator matrix. So this would give me 0 1 1 1 0 and 1 modulo 2 addition. 1 0 0 is just the first row, which is 1 0 0 and triple 1. Okay, so 0 1 0 1 would give me the modulo 2 additions of first and third row. So this is 1 0 1 0 1 and 0. 1 1 0 is modulo 2 addition of first 2 rows, which is 1 1 0 1 0 and 0. Then finally it's modulo 2 additions of all the 3 rows. This will be 1 1 and 1. This would be 0 1 and 0. Okay, so this is a code table. That's what is asked to find, to construct all possible code words. Right. So the last part of this question is, suppose that the received word is 0 1 0 triple 1. We need to decode this received word by finding the location of the error and the transmitted data bits. So this can be found out by the method for the systematic codes. Okay, for systematic codes, the received vector, whatever is given to us, is now 0 1 0 triple 1. This is a received vector at the receiver. We need to find out what is the actual code. So for which we will calculate syndrome. The syndrome is given as S R times H transpose. Okay, so theoretical explanation is given in the last video. R is 0 1 0 1 1 1. Okay, H transpose. Okay, H we have not written. Okay, we'll try to find out what is H. The H matrix, I'll write here the matrix H. How did we represent the matrix H? H, we represented this as, check back with the notation. Yeah, H, we have represented this as PT IM, where IM is identity matrix of the order M cross M, where P is known to us. So P, with that I can directly write this matrix. Okay, this would give me P transpose. P transpose is already written as 1, 0 1. We have done that. So writing that would give me, a minute, 1 1 1 0 1 1. This implies I can take this H transpose. Remember, since I have to write H transpose here, not the H matrix, the H transpose would be constructed as the transpose of this matrix, which is nothing but P IM. Okay, this is again an augmented matrix where the first 3 rows of this matrix would be matrix of the form P. So P we have already written. So P is written as 1 1 1 0 1 1 1 0 0, followed by the identity matrix 0, sorry, identity matrix 1 0 0. Please ask if you have any doubts. Okay, I'm just writing that you know this. Okay, all you need to do is multiply these two matrices to find out what is the syndrome. So the syndrome here, that would result in 0 of the first row and 1 of the second row. It's nothing but second, fourth, fifth, and sixth are to be added with a modulo 2 addition, right? So this would give us 1, okay, and 1 plus 1 is 0, and again 1 plus 1 would give me 0. So this is a syndrome vector that is generated at the receiver. For systematic code, okay, so for especially for systematic codes, okay, we can say that the S is equal to row, S is equal to row of H transpose. Okay, so this is for just systematic code, remember. So S is actually, this is decimal equivalent, so equivalent of S. So decimal equivalent of this S, the syndrome that we have received is 100. So the decimal equivalent of this in this case, okay, S is 4. 100 represents the decimal number 4. So this implies that there is an error at 4th bit of vector R. Okay, so this implies that the actual code word is just obtained by flipping the 4th bit. So received vector is 0 1 0 1 1. We just need to flip the 4th bit here, so which is 1 in our case. So I need to just flip this 1 to 0. This is a 4th bit, and rest everything is same as it is. So this is for systematic code based on its property, that this gives us a simple solution as this. So S directly gives us at what bit position the error has occurred. So this is how you decode what based on the syndrome vector that is calculated. Okay, any doubt in the previous case? Please ask. Yeah, this is the last question that I would take. Okay, and I'll try to conclude the session. Hope you are bearing with me, because we had to combine 2 tutorials, including one of the derivations for binary symmetric channel, based on the derivations that you already done in our offline videos. All right, let me move on to the final question of today's session, and then I'll give you what is expected in test 3, so that it will be helpful to you. Okay. All right, just checking what needs to be done. Yeah, so again, this linear code is given as 6,3, which I have done in one of the examples in case of systematic code. It's the same example that is considered here, but here this is a non-systematic code, or this is known as a linear block code. Okay, so here the same generating matrix is taken, which is IKP, which is K is 3 bits, and P is again a 3x3 matrix. With that, we need to decode based on the received vector R. Okay, this is about decoding technique. So only the difference here would be you would be given different generating matrices matrices and different parity matrices, based on which you will have to, there will be many combinations that are possible. The decoding technique, as I explained in case of systematic code, is to calculate the syndrome, which is R times HT. Okay, so here the R is given as 1 triple 0 triple 0 1 1 times HT. HT that is nothing but that we have done in the previous case. HT is represented as PIM. Okay, in our case, this HT can be directly written here as P is 1 0 1 0 1 1 1 1 0 followed by the identity matrix. Zero, 0, 1, 0 and 0, 0, 1. Multiplication of these two matrices again, what we have done for systematic code. I'll just explain what is the difference between the decoding in case of systematic and non-systematic code. So this is a case with a non-systematic code. I'll just specify this. It's a case with non-systematic code, or this is plain linear block code unless otherwise specified. Okay, so multiplication of these two matrices would result in, this is a modulo 2 addition of first and last two rows. So first and last two rows addition, this give me 1, and this would be 1 1 plus 1, this would give me 0. Unlike the systematic code, I had to just convert this into decimal equivalent, and that would have been the position in the received vector where the error has occurred. But in case of non-systematic code, we know that combination of any two code words in the table would generate another code word in the table. Okay, so with that property of linear block code, I need to find out based on a different approach. We know that this is a syndrome. We know that from theory, the syndrome is due to the error that is caused in the channel, which is represented as E times HT. E is the error vector. I need to find out the error vector in this case. Error vector is the 6-bit vector. Okay, times HT. HT, which I have already written earlier, which is 1 0 1 0 1 1 1 1 0 1 0 0 0 1 0 and 0 0 1. Okay, so with this, the left hand side known to us as 1 1 0, I need to find out the error vector based on hit and trial method. The hit and trial method would give us many results. Okay, that's the reason there would not be any unique solution which would give us what is the actual error that has occurred. According to the rule that I have explained in the theory, that we should choose such an error vector which gives us minimum Hamming weight, or which has minimum number of ones in its row. Okay, so for that we'll try to form a decoding table. Okay, so this is easy to understand once we systematically do it. So this is vector E and this is the syndrome. If this E1 to E6, if it was a 0 0 code, 6 zeros, obviously the syndrome would have been simply 0 0 0. If this error vector, I'll start with 0 weight. Sorry, so I have to start with 0 weight of the error vector. I'll just push this onto the other side. I'll start with a 0 weight. Then I'll go with 1 weight error vector, because I'm finding out that error vector which has got minimum weight. So with 1 weight, I've got plenty of the combinations. Say starting from 1 0 0 0 0, then 0 1 0 0 0 0 0 0 1 triple zeros. Right, so there could be many combinations of this 0 0 0 1 0 0 0 0 0 1 0, and finally 0 0 0 0 1. So all these are error vectors with weight 1. So if I try to find out the syndrome for all these combinations, it's easy to find, where first error vector, which is 1 and followed by all zeros, is nothing but it is the first row of the HT matrix itself, right? So which is 1 0 1. So 0 1 followed by all zeros, this is nothing but the second row of the H transpose matrix, which is H0, second row is in fact 0 1 1. Similarly, the third row is 1 1 0, the fourth row is 1 0 0, 1 0 0, the fifth is 0 1 0, and finally sixth row is 0 0 1. All right, so let me not look at the syndrome right away, because we have already got a solution. But if I try to continue for 2 weights, I'll continue for 2 weights only for the fact that the syndrome S is a 3-bit vector, and I should expect all the combinations of 3-bit vector. Since there are 3 bits, I should have 8 combinations, but there are only 7 combinations of syndrome vector has been generated so far. So what is left over is the only combination here is 111. All right, but I have exhausted all 0 weight and 1 weight error vectors. Then there could be 1 2 weight vector which would result in syndrome 111. So what would be that vector? So that would result in 111 on the left hand side. Can anybody tell the answer? Would I get a unique answer, or will I get more than one answer for the left hand side to be 111? And will there be one unique combinations of E1 to E6, or there would be more than one combinations of E1 to E6 to get on the left hand side as 111? Okay, I guess I have to tell. Okay, there would be not be a unique solution to this. Okay, there would not be definitely unique solution
First,
to this,
fifth,
because
and sixth row, sir.
first, fifth, and sixth row, 1 plus 1. Okay, fifth and
So it
sixth.
should be 1 0 0 0
1.
1 1.
Yeah, perfect. Right, that's good. First, fifth, and sixth row would give me definitely one of these combinations. So first, 3, 4, 5, and 6. And there could be several other combinations as well. But okay, to conclude that point, I'll just come back to the required answer here. So the syndrome here is 110, and I have to find out that combinations of E1 to E6 that would result in minimum weight. So there could be a possibility of only one here, which is 110 I obtained at this part, which has a having weight, or simply the weight as unity, right? So therefore vector E is 0 0 1 0 0 0. So this implies the right code word can be obtained by taking modulo 2 addition of the received vector with the error. Okay, because we know that because the code word which is transmitted from the transmitted is corrupted by the error in the channel, which is resulted in the received vector R. Okay, C is supposed to be R minus E. So in case of modulo addition and modulo subtraction, both have the same meaning, right? And hence I can write C as simply as R plus E. So R, which is a received vector which is given in the question, is that this is a received vector 1 followed by 3 zeros and double 1. So this would give us 1 0 1 1 plus this error vector, which is 0 0 1 triple 0. Okay, so the actual code word which is transmitted is 1 0 1 0 1 1. Okay, so this is the decoding part of the non-systematic code. Okay, so this is what what all expected from the question. But just to move forward and try to understand what I have done as the last part here. So there is a few combinations for which I would get a syndrome 111. Say that if the receiver performs this r times h transpose, the receiver job is to receive a vector and perform this operation r times ht. If for a few combinations of r, we would get a syndrome as 111. Then definitely we can say that the decoder has the capability of decoding not just one bit error that has occurred in the channel, but it can also decode the errors which occur in two places of the transmitted code. All right, so because of the fact that here, what is the minimum Hamming distance? Because since we know that the minimum Hamming distance is given as 2t plus 1. In our case here, the minimum distance between each code, okay, the minimum distance between each code generated in the code table, right? So which is actually is 3. So this implies that it has the capability of detecting and correcting just one bit error. But it is also has a capability of detecting and correcting two bit errors as well. But that will happen only for one of the combinations. Remember, not for all 2-bit error codes.
So I think I gave
Okay.
3-weight syndrome error weight.
Sorry. Oh, sorry. I'm
I
sorry.
think 2-weight some other
Okay.
combination things.
Uh, okay. I'm sorry. Even I didn't look into it. So can you give another other
I think it 1-1.
combination?
Let me see the matrix.
uh, Probably the addition of first and fifth row. This is 1 plus 0 is 1.
Yes, sir.
0 plus
Fourth and
1
fifth
is
also. Oh, no.
fourth
Fourth and
and fifth.
second. Fourth and second.
Fourth and second would give me, right, 0 1 1 and 1 0 0 would be second, right? So second and fourth would give me triple one. Yeah, 0 1 and this is 1 0 0. Okay. So this is just one combination, but there are more than one error vector which would result in one syndrome which is triple one. Okay, but as somebody says, even a stopped clock shows a correct time at least twice in a day, right? So that's the reason I said for other combinations of error vector, if it gives syndrome as triple one and we'll be able to correct two-weight vector, it is true for only one combination of the two-weight error vectors. That's what I was trying to explain. All right, so this is what is all about block coding for systematic and non-systematic codes. So you would be just played around with the generator matrix, and you'd be asked to find out the code words and find out for the given received vector, you'd be asked to find out what is the actual code that is transmitted. All right. So as a final note of this session, that I would explain what is expected in the test, uh, which starts from tomorrow, as far as CS1, CIE3 is considered. Okay. So the syllabus for obviously it's known to you. The syllabus is complete unit 4 complete, and unit 5 up to linear block coding. Okay, we are just left with just 2 to 3 classes to complete Unit 5 that I'll take online once you finish your tests. I will not just continue with just recording videos and sending across, which I don't feel comfortable. Anyway, so the test would cover uh, both theory as well as numerical based type questions. So theory would cover whatever we have done as the derivation of channel capacity, which is actually Shannon's rate equation. Okay, so we did for both continuous and discrete. So and hence it could be both for discrete memoryless source and continuous memoryless source. Okay, please go through the derivation part of the channel capacity. Okay, so that's about that. And you would also would be given a question based on binary symmetric channel, binary erasure channel that we did in today's session. uh, Binary erasure channel can be derived similarly with respect to binary symmetric channel as well. I mean the derivation of channel capacity for these two cases, specific cases. Right, so that's about the theoretical aspect as well. And the third part, of course, is on applications of applications of Shannon's equation, applications of Shannon's equation onto practical communication system. That is the last part of Unit 4, practical communication systems. Practical communication system. So based on theory, you would be asked these two, and numericals would be numericals based on this would be I'm sorry, there was a call. Yeah, the numericals will be based on whatever we have done today. That, to make it more clear, this would be based on could be calculation of entropy, conditional entropies, and so on. Calculation of entropy. Okay, the mutual information, the capacity, and so on. Right, we did it as one of the questions in today's tutorial session. The second would be definitely we did not cover in the last test, Shannon Fano coding. There will be one numerical based on Shannon Fano coding, which is pretty straightforward. You would be asked to calculate the entropy and the efficiency by finding out by using the Shannon Fano algorithm and encoding for the sources. And of course, as the last part, there will be numerical on block coding. Okay, so this would comprise your 5 questions of your test. As far as test is concerned, the quiz will revolve around mostly on numericals and some of the concepts that you have studied based on information theory. Okay, so if you have any other questions, you can ask me. Otherwise, you can start preparing for the test if you have not yet started. Okay, hope I am clear with that. Thank you for having your patience, and almost we are 2 hours to actual schedule the explanation that we have planned earlier. It's almost 3:30, but I thought, extending this session based on the fact that tomorrow itself is your CS1. Probably from this point onwards, you will start preparing for the test. Hopefully, it will be good for you to prepare. If I take a little more time and to explain what is expected in test 3. Right. Yeah. Thank you, everyone. We'll
Yes,
meet
yes,
after
sir.
that.
Thank you.
Meet after the test. And this test, I promise that it's much simpler than your first two tests combined. So probably there are pretty straightforward questions as well. You need not worry. Okay. And the derivations are already available with you as ready-made notes. Please make use of them and score good marks. Yeah. Thank you and good luck to all.
Thank you, sir.